Alrighty. So this is where we're talking about the damping factor. So basically the idea is, if you take the product of two different functions, what will happen when you try and graph those? So like here in the example, you can see we're looking at x times sine of x. So, of course, we're looking at the product of two functions. You have the y equals x function and the y equals sine of x. Now, remember with sine of x, we know that the range of the sine function goes from -1 to +1. So that's kind of what they're talking about here, is that if you look at the absolute value of sine x, it's going to be less than or equal to 1, which basically translates as sine of x is going to be less than equal to 1 or less than equal to -1. So that's what this little statement here is saying. So they're saying if we transfer this over with the x times a sine of x functions, and basically this is what that inequality will end up looking like, because you're taking that factor of x and multiplying it on all sides. And again, if you clean that up, it's going to rearrange to this format here. So we're basically saying your x times sine of x is actually going to be sandwiched between absolute value of x and negative absolute value of x, which basically means it's going to be between these lines of negative x and positive x. Now, if you try to graph these, these are going to end up looking like a cross, because this line here will represent y equals x. This line here will represent y equals negative x. So that's what they're saying, that the graph of our function x times sine of x is going to lie between the lines negative x and positive x. And then, because the sine function has its maximum and minimum values, it has its intercepts. Again, if you kind of think about those key points in the sine function, based on that, you will actually see that your x times sine of x function will be equal to positive or negative x at the value of x, which is pi halves, and multiples of pi halves. So pi halves plus n times pi, moving it around 180 degrees. And the function x times sine of x will be 0 when the x value is just going to be n times pi. And this happens, and you can kind of see the note right here. This happens because your sine function, where did that go? Yeah, there we go. Because the sine function itself is going to be equal to +1 and -1 at odd multiples of pi halves. And it's going to have the x-intercept or 0 at multiples of pi. So that same behavior, kind of translates to the x times sine of x function. So, again, the graphs of these damped functions are going to be based on, properties of these individual functions. So what does the x function do and what does the sine of x function do? So that's why you will see this is kind of what this graph ends up looking like. So here you can see this line with the positive slope is your y equals x line. This line with the negative slope is your y equals negative x. So there's that cross we were talking about. Now, normally, your sine function has this sine curve. So what happens is you will see, instead of, staying in that -1 to +1 range, that range will change because of this damping factor of x that we have. And it still has that general sine curve, but now, it's going to be bounded by these lines, y equals x, as these lines will grow, your function is going to keep going in that direction. So that's kind of what that damping factor does, is change, those graphs. And then you will see that, of course, where did I go? There we go. So you've got another example over here in example 6. This time you have x squared with sine of 3x. So those would be the two functions we are talking about. So same kind of thing, what will each of these function behaviors change when we try and graph them together. So they're again kind of going through that same explanation here. And then they talk about, how your function is basically going to be bounded by negative x squared and positive x squared. So remember, positive x squared is a parabola that opens up. Negative x squared is a parabola that opens down. And then, of course, we know sine of 3x is going to be where, your period of the function changes because of that b value of 3. So imagine what the sine of 3x function would look like, or, put it on a graphing calculator to see what that function looks like, just to get an idea. And then how will this damping factor of x squared change that? And so again, if you come and look through at the graph over here, you will see right here on the top is our positive x squared. Here is our negative x squared function. So again, you can see how that sine curve again gets bounded by these parabolas opening up and down. And you can again see, we're going to touch the surface of these parabolas. You're not going to go beyond that, right? You're going to stay where that curve is, and you're going to touch that point, and then you're going to turn around, touch that point. And as you keep going down, that function is just going to keep going in that fashion. So that's kind of what these damping factors do. If you want to see again what difference you can see with the x squared sine of 4x, you can again see this in your video lecture to break that down. And I think I did show you guys this summary last time. So let's pick an example from our textbook here. So this one I thought was kind of a neat exercise because they're giving you these graphs here. So there's 4 of them, and they're basically asking you to match it with the function itself. So, you kind of have to see, okay, what is the general shape of these functions and what the damping factor might be, and based on that, choose your function here. So these are the 4 functions. You have absolute value of x times cosine of x times sine of x, absolute value of x times sine of x, and an absolute value of x times cosine of x. So, of course, imagine what kind of behavior the damping factor is going to have. Now, when we talk about the line x, of course, we know x is a line with a positive slope that goes up. When you're talking about absolute value of x, well, for absolute value of x, if you guys remember, that has that V shape kind of thing going on for it. So based on that, just to kind of get us started, and let's see if I can try and get this on the same screen. Okay, doesn't look like that'll happen. Okay, so we have absolute value of x cosine of x. Okay, so that's one function, x times sine of x. Okay. Absolute value of x sine of x, and then the last one was absolute value of x cosine of x. Okay, there we go. Okay, so between A, B, C, and D, which graph would you, which function would you choose for which graph? So I'll give you guys a couple seconds to kind of look through that, see what you are leaning towards, and then we'll have you share your answers through chat. And since we don't have, what were these question numbers, 61 through 64? So just basically tell me, 61 goes with, A, B, C, or D, you know, what does 62 go with? So just in that format, you can share your answer with me to see which function goes with which graph. Okay, so take a couple seconds, match your graphs with the function, and then when I ask you to, you can share your answers with me through chat. So just get your answers ready. Don't share it just now. Alrighty, guys, go ahead and let's see what matching answers you came up with. Alrighty, Savannah, I see your answer. Okay, what about the rest of you? What did you think? What are the pairings? 61 goes with which graph? 62, 63, 64. Okay, so I'll share the answers that I've gotten right now. So let's see, we've got 61 with C, 62, with B. Let's see, 63 with A, and 64 with D. Okay, and then the next answer that I came up, I see on my chat here is 61 with D, 62 is B. Okay, so both of you went with that. 63 is A, and I have a C also, and then 64. Okay, Lucy, so it looks like you're actually using your B twice for 62 and 64. And then Darren, you have A. So D, B, C, and A. Okay, I see that. Alrighty, so let's take a look at this. You have, and we're going to go in the order of the functions themselves. So for part A, you can see that this one obviously is a sine curve. And the reason we know that's a sine curve, because at the origin, you will see we are at the intercept. Remember, the cosine function starts at a maximum when the x value is 0. So you can kind of use that also. The other thing you will notice here is also that even though you don't see those lines, you actually have those y equals x line here and y equals negative x. So actually 62 is the function that goes with A. And this is the same function that we talked about right here with the x times sine of x. The only difference that you are seeing in your textbook actually is they are only showing you this little portion of the graph here. But it is the exact same function that we did right over here. So I know it kind of looks a little bit different, but that's exactly what 62 goes with A. All right, let's go on to part B over here. And part B is what looks like all of you assigned 62 with. So, obviously we know that guy was incorrect. That should have been A. And then Lucy, I think it might have been you that did 64 with B also. And if you look at the 64, the B graph over here, again, I know it's kind of hard to see, but you can kind of imagine that this is where actually that absolute value function is going to be, because part B actually goes with number 63. And the reason we know that 63 and not 64 is because, again, at the origin right over here, you have an x-intercept. And again, we know the sine function will have an x-intercept at the origin. So again, just with the shape of the way that graph is, and this is the part where it can get a little confusing, because your V opening up and down can look very similar to an X that you're getting from the, X times sine of X, or the absolute value of sine of X. But the only difference between graphs A and B is you're going to see how different that sine curve ends up looking like. And that's because, your function is going to obviously behave a little bit differently based on that. So this may be another portion where, instead of trying to, draw these graphs by hand, I would probably use technology to make our life a little bit easier. So this guy, graph B, is actually going to go with function 63. And looks like you guys had gone with C and A, which of course did not come out to be our choice. That's going to be graph B, which will then bring us down to, let's pick a different color here. We'll do orange. Let's do graph C over here. So now with graph C, we are obviously left with choosing between 61 and 64. Does anybody have an idea which one would seem more appropriate for C, 61, or is it 64?
My guess would be 64, since that goes into the negative.
Again, if you look at graph C over here, you kind of have to imagine, again, what kind of shape is this going in? Of course, the two options that we are left with is now, going to be both cosine and cosine. The only difference is you have absolute value around x on 64, and you have the absolute value symbol around the entire function. So that is definitely going to change the behavior between our graphs. So graph C actually does go with 64. And again, you are actually going to have that V shape of the absolute value, opening up and opening down. And even in this case, you will see that it looks like, we have a x-intercept over here at 0, 0, but that's again because of that damping factor, your oh, the word just flew out of my mind. Because of the damping factor, basically, instead of having that maximum, which is kind of where the cosine function begins, right? What's happening is, because of that absolute value, it's actually going to get pushed downward. So you won't have that +1 where you can have the maximum value on a cosine function. So that actually does get switched because of your damping factor, because of that absolute value of x. So yeah, very nice. Lucy, we do actually end up with graph 64 or graph C with the function 64. So this guy is going to be with C, which of course, you know, process of elimination, that only leaves you with D for 61. And this one, because the entire function is in absolute value, well, if I do that, then all of these guys kind of get misplaced, and that doesn't help. Well, in this case, it's kind of hard to picture that, but this is kind of where your absolute value, you know, that V form is going to be right at the top. And of course, if you can see, we don't actually have any part of our graph that falls below the x-axis, because since your entire function, x times cosine of x, is within the absolute value symbol, you're actually not going to end up with any negative y values, because no matter what you do over here, this value is always going to come out to be positive. And that's why you have no graph below the x-axis. So that's actually another clue of how you would have known that your function here is going to be graph D, is because we know our y value is always going to stay positive. So it can only be the function, you know, where the graph is above the x-axis, where all the positive y values are, and there's no function for the negative y value. So, you know, some of those tricks that you had in algebra, you can still use those to help you out here. And like I said, when you're in doubt, you know, use a graphing calculator. You can just plug these guys in Desmos and get help from there. So that definitely works out in this case, because these damping factors, if you try to do them by hand, can definitely be a little bit challenging. So I definitely recommend using technology. Like, look at these. Was this the example I was looking at? Yeah, I think so. So if you look at these examples over here. So this one is saying, you know, use a graphing utility to graph the function and the damping factor of the function in the same window and describe the behavior as x increases without bound. And I think they actually had asked us to do that here also, is describe the behavior as x approaches 0. So, you know, of course, in this case, you would kind of have to see what behavior is your graph doing as it gets closer to the origin. And of course, in both cases, you can see when x value is getting closer to 0, your y value is also getting closer to 0. That's actually true for graph C, and that's also true for graph D. So for all 4 of these functions, we can basically say as x gets closer to 0, your y value is also getting closer to 0. So that's actually true for all 4 of these graphs over here. Now on these functions, they are basically saying, you know, what happens when your x increases without bound, which means what is happening as your x gets closer to, you know, positive infinity or negative infinity. So how about we try out, let's do 69 and 71. So you can kind of see, you know, what happens when you have the pi of x on your cosine function, and then we'll do one with the x to the 3rd power. So that way we'll get a good idea of what both of these functions will end up looking like. So let's open Desmos for that. We'll go to Math Tools and Graphing Calculator. And then we are doing x times cosine of pi times x. Okay, so for now, I'm just going to remove that x in the front, the damping factor. And you can see this is exactly what we expect from a cosine function. You will see you're starting out right at the center. You are starting out at a maximum, intercept, minimum, intercept, maximum. And the only difference is because of that pi, you know, the period of our function is going to change like we saw in the previous example. So this is definitely the behavior we expect from a cosine function. If I were just to graph the x by itself, we know that's going to be a straight line with a positive slope, going from left to right, it's going to go up. So now if we try and take this line and mix it with our graph, look how the the cosine function changed. And you can see I still kept that graph in the blue because, in the red, the x actually becomes an imaginary line, so you don't actually get to see it. Now let me go ahead and graph the negative x function also. And you can see how your cosine of pi of x function is bounded or is restricted by the positive x and the negative x line. So, it kind of makes that visualization a little bit better. And this is what's happening in all of those 4 examples that we saw before. So as you can see here, of course, when you get closer to 0, you can see even in this function here, as your x value gets closer to 0, your y value is also getting closer to 0. But they were asking us what is happening when the x value is getting closer to infinity. What is your y value doing? And as we zoom out, you can see what this graph ends up looking like. So can you guys tell me, what do you think is happening as that x value increases without bound? So basically, as x is going to positive infinity and as x is going to negative infinity, what would you say? What is your function behaving like?
The periods are getting smaller.
Scott, would you say that one more time, please?
The periods are getting like smaller.
Yeah, the period will definitely change because of the pi of x with the cosine function. But what else do we notice with those y values? And if you want to see that visualization again, let's clear this out. There we go. Because what's going to happen here is, and I know it's got that cosine curve, so maybe that's making it harder to understand, but yeah, very nice. So Andrew, you said as x goes to infinity, y goes to infinity. Savannah, getting bigger as well. And the same for negative infinity, Andrew. Yeah, so what's happening is you're still seeing that oscillation happening, right? Those sine curves that we expect to see with the sine and cosine functions. So that's still happening. But eventually you will see how if we just go down, your y values are getting smaller and smaller on the negative side, right? So eventually you will actually start approaching negative infinity. On the other side, if you go on the upper half, you will see as x is going to positive infinity, well, your y value will also, it's going to take its time because it's going to do that oscillation, but your y value is also getting larger and larger. So it is going to approach both positive and negative infinity for x. So basically, I would say as x approaches infinity, y value approaches both positive and negative infinity. And same thing as x approaches negative infinity, y approaches both positive and negative infinity because of that, that x shape that's coming from that positive x, negative x. So if we make this guy smaller, you will see basically it's going to keep doing that on both directions. So that was our x times cosine of pi x, and you can kind of see that same, well, a very small version of that graph over here. Now let's look at 71. So this is x to the third sine of x. Well, we know sine of x, again, is going to be your normal sine curve starting at intercept, x-intercept. And of course, in this case, as x goes to 0, your y also goes to 0, for that one. But we want to know what happens as x is going to positive and negative infinity. But before we can do that, we need to do our damping factor. And remember, this one is x to the third power. So look at the graph in black. That's the x to the third power. So look at how it has that, you know, it's a cube function, right? So it has that odd function properties to it. Now, what will happen when we put that damping factor of x to the third with our sine function? And you can kind of see it still follows that curve in the black because, you know, it's getting bounded by that. Now let's go ahead and put a negative x to the third. Which is that graph in red. And you will see how over here, you know, this part of your sine curve is getting bounded by the positive and the negative x to the third power. And then, you know, let's go ahead and zoom in, sorry, zoom out so we can see a little bit more. You know, again, it's kind of weird the way that is, but you know, as these oscillations of the sine curve hit the x to the third or the negative x to the third, you know, that's where it's going to stop and then turn around and, you know, keep doing that oscillation factor. So what would you say your y function is doing as x goes to positive infinity and as x goes to negative infinity?
Do they both go to plus or minus infinity?
They both go to plus or minus infinity. Do you guys agree with that? Yeah, because the only difference is going to happen is, you know, you're not going to see that x formation that you saw in the previous graph because you're in the previous graph because your damping factor is now x to the third and not x. So that definitely makes a difference on the way your graph is going to do. But yeah, that oscillation is still happening. As you guys saw over here, you know, when we zoom out, you can still see that oscillation happening. But you know, eventually as x goes to positive infinity, your graph, your function, or the y value will also start approaching positive and negative infinity. So same kind of behavior as the last one. For both of them, your y value will be approaching positive and negative infinity. And of course, you know, you will still see that oscillation behavior in your graph. And just to show you very quickly, you know, as you change that damping factor, you know, if I change that to a square, the graph is going to change. So again, change this guy to a square, change this guy to a square, and look how the graph will change. You know, that sine function is going to change a little bit. So the damping factor is definitely going to affect what your sine curve will end up looking like. You know, of course, we saw with the sine function, what that ends up looking like. You can see again how with that damping factor, your sine curve changes. So you can definitely play around with different damping factors and see what it's going to end up looking like. And again, you can kind of see that generic shape over here in this screen. Okay, any questions on this over here, guys? So for this one, like I said, use graphing calculators instead of trying to graph these by hand because graphing by hand can be pretty tedious for these guys.
So I had one exercise that was like asking to graph like sine minus cosine or something. Is that just something I should do with a graphing calculator?
That was from 1.6.
Yeah.
Okay. Let me go into our homework. Like something like number 23.
Yeah, that might have been it. Yeah.
Because this one is just asking if the function is odd or even. This is where the damping ones come in. So you can see this is the absolute value of sine x, and we looked at that in those matching graph one. So that's where this is coming from. We did the absolute value of x times cosine. I think this might be the one.
Yeah, this is it.
This is it. Yeah, so for this one, I would definitely go with a graphing calculator because again, trying to graph the sine of x minus cosine of x plus pi halves by hand will be very tedious. So for these ones, I would definitely ask you guys to use the graphing calculator. And you can see they're actually having you graph the f of x and the g of x functions together. And then they're having you see, well, what kind of comparisons do you see between the two graphs? And this one kind of is following that same thing here. They're having you graph both the functions and then see, over here, they're asking you how similar or different they are. So, they're kind of bringing in that idea of transformation also in these and trying to see, is your graph moving up or down, left or right, or are you seeing that phase shift or those kind of things? So yeah, for these types of functions, even for this one over here, I would definitely ask you guys to use the graphing calculator. And if you don't have a physical handheld calculator like you saw me bring up the Desmos calculator over here, that's what I would do. And as you can see with Desmos, you are able to graph multiple functions on top of each other. So you should be able to graph both the f and g functions and then pick, which one is going to be, where did that go? Which is going to be the right graph.
For the exam, do you expect us to use a graphing calculator?
For
some
these
of them?
ones, yes. And the other sort of the sad thing about working with a function like WebAssign is you don't actually get to graph your own function, right? Because
Yeah.
they just have you choose, kind of like you're seeing on your screen right now, they just have you choose between the right one. So since we don't have the option of graphing our own functions, I'm okay if you guys need to depend on a graphing calculator for that.
Is it okay if that calculator is Desmos?
Yeah, yeah,
Okay,
you should
cool.
be able
Thank
to
you.
have access to Desmos on the exam also.
Sweet.
Because I haven't done any restrictions on your browser or any of those setups, so you should be able to use the Desmos graphing calculator. Any other questions coming to mind on this, guys? Okay. So as you are finishing the last part of 1.6 homework and you do come up with any questions, obviously don't hesitate to reach out. You can send me an email if you want to ask me on Wednesday's class, any of those would be fine. Okay, so to get used to some terminology, we have used the main trigonometric functions, right? Sine, cosine, trig. We have talked about the reciprocal functions for trig, which is where the secant, cosecant, and cotangent come into play. So remember, you have the main trigonometric functions, then you have the reciprocal. Now we're talking about inverse. And the unfortunate thing is in English, the language English, we sometimes use reciprocal and inverse like they're interchangeable. But here in math, they can mean two completely different things. So when we're talking about inverse trigonometric functions, please remember we are not talking about secant, cosecant, cotangent. We are literally talking about this inverse symbol over here, or sometimes we call them as arc sine, arc cosine, arc tangent, or we use this symbol and that little exponent of -1 that you can kind of see over here. This is the inverse function notation. So you guys might remember that from your college algebra class when we talk about inverse functions. So this is kind of where those inverse, terminology is coming out from. And the other thing I wanted to show you, we'll do our little TI calculator here just to show you what those calculator functions will look like. Oh, I hope this is going to be a bigger image. I guess it'll have to do. So where you see your sine, cosine, tangent functions, right above that, you should be able to see the sine inverse. So it looks like the sine inverse, cosine inverse, tangent inverse. It's going to be, you will have to use the second key to get to these inverse functions. Now, if you are using like a TI, 84, one of those graphing calculators, I think you have to go under a menu option to get to the sine, cosine, tangent, and the inverse functions. But basically, those are the functions we are talking about. So just please remember the difference between cotangent, secant, cosecant, and then these arc sine, arc cosine, arc tangent functions. Alrighty, so let's take a look over here. So one thing you should remember about inverse functions from college algebra is that an inverse function will undo what the original function does. So very simple, subtraction is the inverse function for addition, right? So if I did 2 plus 3, I get 5. If I did 5 minus 3, I go back to 2, right? So that was the inverse function. In that same way, division is the inverse for multiplication and vice versa. Square and square root are inverse functions. So in that same sense, when we're talking about inverse functions here in trigonometry, we are talking about what the sine function will do. The arc sine function will undo that, okay? Some of the other properties that you may remember from inverse functions is, of course, your inverse function and the original function itself has to be 1-to-1, which means that if you draw a horizontal line through your function, it will only cross the graph at one point. And obviously, you will see here, when we look at the sine function and I draw the horizontal line test, it actually crosses at 2 point, which, of course, if you keep going, every time you have that little sine curve, this line is going to cross all of those, points. So the idea is sine function by definition is not a 1-to-1 function, which technically means if you are not a 1-to-1 function, you do not have an inverse function. So this is kind of where we bring in this idea of restricting the domain. So we will say, let's restrict the domain of the sine function and only go from negative pi halves to positive pi halves, which is that area in black that you are seeing in this, because this is your negative pi halves, this is your positive pi halves. So if we restrict the domain, we say the x values can only go between these two numbers, including them, so that means none of these parts of your graph exist. And if they don't exist, then if I draw a horizontal line, it's only going to cross at one point. If I draw a horizontal line, it only crosses at one point. So by restricting the domain, we are actually able to create its inverse function. So, here you will see on the interval negative pi halves to positive pi halves, your sine function is increasing because obviously, as you go from left to right, your y values will become larger. They are also saying from negative pi halves to positive pi halves, you are getting a full range of your y values because right here, you have -1, which is the lowest value for our range. And at this point over here, you have +1, which is the highest value for our range. So you are getting a full range of values going from -1 to +1. And like I said, on this interval, our function is also 1-to-1, which means we say our function is invertible. I spelled that wrong, didn't I? It's invertible, which means you can find its inverse. So it has to be 1-to-1 because without that 1-to-1, we cannot find inverses. So that's kind of what happens when we restrict our domain between these two values over here. Now we are saying on this restricted domain, your y equals sine of x function will have a unique inverse function, which is of course what we call as an inverse sine function, and you call it arc sine, or like I said, use the inverse notation by putting that sine to the -1 power. Now remember, that is not an exponent, guys. This is just a notation that we use for inverse function. So you're not saying, like, you know how we say sine square of x, which means it's sine of x times sine of x. This is not the same thing. This is not a negative exponent, kind of like, you know, when we do a to the power of -1, you get 1 over a. This is not that either. This is just a notation we use for inverse functions. Or like I said, if you want to avoid any confusion, just go with the arc sine definition instead of the inverse symbolism if you don't want to do that. Now, what's going to happen in this case, and just another thing from algebra that you can remember is when you look at a function and its inverse function, remember your domain and range switch places. So for the sine function, which is the domain, will actually now become the range of the inverse function. And for the original sine function, what is your range, will actually become the domain for the inverse or the arc sine function. So basically your x and y values switch places between the original function and its inverse. So all of those properties, and if you need to go back and review inverse functions from algebra, you know, go ahead and do that. They're also telling you, you can go to chapter P, it's section P.10, where you can review inverse functions if you want to do that. And then as you can see, there's some more details there, including over here, they're saying, you know, the notation arc sine comes from the association of the central angle with the intercepted arc length of a unit circle. I mean, if you want to get into some of that in-depth theory, you can. I didn't include a whole lot of it here, but basically, a lot of the things to remember is now you will see the values of arc sine are going to lie in that same interval that we chose to restrict our domain on. So we are saying the arc sine of x is going to stay between negative pi halves and positive pi halves, which technically becomes the y value of this inverse function. So remember, this was the domain for the sine function. It has now become the range for the arc sine function. So that's kind of what I was talking about, that interchange happening between domain and range. And this is what the graph looks like. If you remember with, let's see if we can go back to Desmond's. If you remember with inverse functions, when you look at the graphs, they are reflections of each other with respect to the line y equals x. So let's go ahead and do that. So this is your line of reflection, the y equals x. So if I did an x square function, and can I restrict this to x greater than 0? Okay, it's still not doing that. Well, let's do x squared, and then let's do square root of x. Okay, since I am unable to restrict our domain, you want to ignore this part of the x squared function. So if you look at, this is the line y equals x, which is our line of reflection. And if you look at the curve, which this guy here is the y equals x squared, this guy here is the y equals square root of x. You will see if you take this point over here, which is going to be the point 2, 4, this point actually ends up reflecting right over here, and it becomes 4, 2. So you will see how your x and y values have interchanged. And that is just the easiest point for us to pick on. You can obviously pick any point. You will see both of these are intersecting at the same point, 1, 0. or, you know, on the reflection side, that will become, sorry, not 1, 0, 1, 1. And even when you reverse that, it still stays at 1, 1. So this point really does not work. So that's why, you know, the 4, 2 and the 2, 4 work. So this same thing you are actually going to see with your sine and inverse sine functions also. And, you know, again, since I am unable to restrict that domain, we're just going to do the sine of x function, and then let's do the arc sine of x function. So if you zoom in, you again want to remember, restrict your domain between negative pi halves and positive pi halves, which will be about 1.57. So you are again kind of ignoring, you know, again, I'm kind of eyeballing this, but you're ignoring all of this graph here. And you're kind of ignoring all of this here. So then you are again, you know, if you see with respect to that line y equals x, you can see how this curve is a reflection with respect to this curve. So those properties, you know, again, are all going to stay with these inverse functions. So a lot of the similarities that you saw in your college algebra course are still going to be part of, you know, these functions over here. So if you just look at, and I know they're kind of separated, but if you look at this curve over here, this is the reflection of that sine curve, which is restricted between negative pi halves and positive pi halves. So just as your definition, you can see how your domain and range are switching. So we are saying the inverse sine function can be defined as y equals arc sine of x if and only if we can say that the sine of y is equal to x. And this relationship here, guys, is going to be very, very important. Because we are basically saying if you have y of arc sine of x, basically think about this. If I multiply both sides of my equation by the sine function, you end up with sine of y, which is what we had over here. And then because sine and arc sine are inverse functions of each other, you know, it's kind of like how square and square root cancel each other out. You want to think about this in the same way. The sine is going to undo what the arc sine does, and you will just be left behind with the x. So this relationship between the arc sine and sine function is going to be very, very important, because you will see examples, and those of you who've already worked through 1.7 homework, you've already seen this, how they are having you use this inverse relationship to help you come up with, you know, values for x and y and those kind of things. So this relationship here is going to be very crucial that you need to know. And then the other thing, of course, is here for the arc sine, you can see your domain is going to be between -1 and +1, and your range is going to be between negative pi halves and positive pi halves. However, for the sine function, remember for the sine function, this was the range. And for the sine function, this was the domain, or the restricted domain, if you will. And you can see that over here in this graph also. You will see how for the x values, you can see the leftmost point is at -1. The rightmost point is at +1. So that's your domain. -1 to +1. And then you will see your range goes from negative pi halves to positive pi halves. So that's kind of what they're talking about. So as you can see, they're having us evaluate some possible answers over here. So just to go over these very quickly, you can see they're asking us to find arc sine of -1/2. And, you know, they're kind of using that relationship. Well, sine function at -pi/6 is -1/2. So when I do arc sine of -1/2, it's going to come out to be negative pi over 6. You know, for some of these things, you can get from the unit circle. Some of these things you may be able to throw into your calculator, you know, especially if they need the exact answer with the pi and, you know, the square root values and stuff, you probably want to use your unit circle more than you want to use the calculator. But we can take a look at some examples for that here in a minute. If you look at the graphs for the arcsine function, they're just kind of walking us through the steps over here. Remember how your domain and range has switched. So in this case, you almost kind of want to work backwards. You start by picking your x values, which represent the sine of y. And then working backwards, you can figure out what your y values are going to be. So using it, you know, kind of in a reverse order. So they're saying, you know, okay, you're going from the interval of negative pi halves to positive pi halves for the y value, but think of those as the x values for the sine function, and then think what your y values are going to be. So, you know, again, you're doing that interchange. And if you remember from college algebra, we would usually say, okay, let's do the x and y for the sine values. So, you know, at negative pi halves, at 0, at positive pi halves, what are your y values going to be? So of course you can see at negative pi halves, that would be -1, you know, 0 of course would be 0. At positive pi halves, it would be 1. So if you do this for the sine function, well then for the arcsine, just switch that. So the negative pi halves will now become the y value, positive pi halves, and then, you know, literally you are interchanging your x and y columns for the arcsine function. So still using that same techniques you saw in college algebra, come up with the table for the original function and then switch the x and y values and you'll get the table for the inverse function. So, and you know, that's great because you're not reinventing the wheel, right? You're just using the techniques you learned in college algebra and applying those over here with the trig functions. You know, of course, this one here is talking about how you can use the graphing calculator to do a comparison between sine x, arcsine, and use the line of reflection y equals x. And I already showed you that. So how you can use that to do a comparison. What did I do? There we go. Okay, so that was your sine function. Now we can talk about cosine, which as you can imagine is going to be the same thing. We are going to have to restrict our domain, but this time for the cosine function, your restriction is going to go from 0 to pi. And so you can see that would be this again, the shape that you see in the darker black color. So that's going to be our restricted domain. And then again, you know, obviously you will go from +1 to -1 over here. So you are getting that full range of the y values. If we restrict the domain, we of course have a 1-to-1 function because your horizontal line will cross the graph at only one point. So all of those properties that we need. So the inverse cosine function again is what we would call as arc cosine or inverse cosine. As you can imagine for the tangent function, we will again restrict our domain between negative pi halves to positive pi halves, and then your inverse tangent function is going to be arc tangent. So again, you can kind of see that summary of the three inverse functions over here, what their domain and range are going to be. Because the tangent function, if you remember, you know, kind of has this shape where you have those vertical asymptotes kind of thing. That's why you will see the domain for the arc tangent is going to be -infinity to +infinity, whereas for the arc sine and arc cosine, you know, because they're those oscillating curves, this is going to be between -1 and +1. So just, you know, again, do that comparison between your tangent, cosine, and sine functions, and you will see how these inverse functions come out to be. And here is, you know, just a nice graph to kind of show you when we do those restricted domains, what your inverse functions come out looking like. So let's pick a couple examples like these ones here where they're actually asking us to find the values for arc sine, arc cosine, arc tangent, and those type of examples. So let's go back into our homework here. Okay, let's do these ones here. So they're just asking you to find the exact value, so not a decimal answer, the exact value for these, and we'll do one of each. Let's start with number 14 over here. Arc sine of square root of 3. You can think of that as equal to y, if that helps. So if this is arc sine of square root of 3 equals y, then basically you have to think about, okay, so sine of y equals square root of 3. So for what value of y would my sine function be equal to square root of 3? And while you guys are thinking, let me see if I can open up our unit circle. So where will the sine function, or for what value of y will the sine function be equal to square root of 3? So take a minute, think about it. I'm not sure if this is really working out. If this is looking kind of weird for you, go ahead and open up the unit circle at your end. Again, you can just go to D2L, go under content for chapter 1, and you should be able to find it. So what can we do to find the y value for which sine function is equal to square root of 3, or basically arc sine of square root of 3 will be equal to this answer? What do you guys think? I'm not seeing any answers come through. Do you find anything where you think that could be a possibility?
No.
No, because you will see for all the, yeah, Savannah. So yeah, you can see for all the sine. And remember, guys, the way these ordered pair works, the first one is the cosine value, the second one is the sine value. So even if you look at these, you can see there's square root of 3 over 2, square root of 3 over 2. And then these guys are actually getting into negative values, so we can't really even use these. And you can see this is not just square root of 3, this is square root of 3 over 2. So by looking at the unit circle, obviously nothing is going to jump out at us. Let's get here. So in this case, you will actually see there is no value. And what happens if you just try to plug in arc sine of square root of 3 in your calculator? What does your calculator tell you? Just so we're double. Yeah, it's going to give you an error. Android gives you a domain error. Yeah, let's see if we can go into our little Desmos guy over here. We'll just pick our little scientific calculator. There we go. So we are doing sine inverse, which is our arc, and then square root of 3. And you can see we're already getting undefined. Does anybody know why you got a domain error or why it says undefined? Well, what is the domain of our sine function? And what is square root of 3 approximately equal to? Yeah, very nice. Square root of 3 is approximately equal to 1.7, which is beyond the maximum value that your domain can have. And that's the reason why we don't have arc sine of square root of 3 value. And that's why, Andrew, you got that domain error, right? Because it's outside of your domain range. So that's kind of what's happening over here. So, just small little thing, but a lot of times we don't really think about those because, we haven't had to think about a restricted domain up until this point in all of our discussions. So because of this is going to be undefined, or I'm not sure what WebAssign has you guys type in. It may have you like DNE or something like that. It might have you type it in there. DNE does not exist. So, that might be one of those options it has you type in. I'm not sure. So be careful about, those domain and range restrictions when you're working with these functions. Question on this one, guys? Okay. Okay, so this was arc sine. Let's pick an example with arc cosine. Arc cosine. Let's do number 10. Okay, so arc cosine of 1/2, same thing, we'll set it equal to y. So then we can basically say, well, cosine of y has to be 1/2. So again, what y value are we leaning towards? And this might be kind of superimposed also, but let's see if that works out for you. So where is the cosine value? For which angle is the cosine value equal to 1/2? Savannah, yeah, very nice. So you will see, again, remember cosine is the first value in your ordered pair, and you will see right over here is where we have cosine of 1/2, and that is going to be at this angle. And I know it's kind of hard to see, but that is pi over 3. Because as soon as we move over to the other side, you will see this ends up becoming negative 1/2. So obviously that guy does not work. The only other side you would have is positive 1/2 would be down here at the angle of 5 pi over 3. But that's obviously a multiple of pi over 3. So you want to go with the first angle that you can possibly come up with. So that's why we are going to stick with pi over 3 in this case. So let's go back over here. Let's get rid of this guy. And so this one here, cosine of y equals 1/2 when your y value equals pi over 3. So that means arc cosine of 1/2 will be the value of pi over 3. And that was for number 10. So you can see some of these, like I said, you can literally fall back on the unit circle to help you come up with these answers. And we know 1/2 is within the domain of your arc cosine function, because again, you will see your arc cosine has a domain of -1 to +1. So 1/2 obviously falls within that domain. So that's why we knew we would be safe with that answer. So arc sine, arc cosine. Now let's do an arc tangent. Let's see, we have tangent inverse of -3, sorry, negative square root of 3 over 3. Yeah, let's try that one. So tangent inverse of negative square root of 3 over 3. Again, that is the same thing as if we said arc tangent of negative square root of 3 over 3. So that means we are looking for where tangent of y would give us -3 over 3. Now, if you wanted to use the unit circle for this, you can, but remember, you will not be able to find the answer directly. So what you would have to use in this idea is when we say tangent of y, that means you're looking for sine of y divided by cosine of y. And that should give you negative square root of 3 over 3. So that is how you would have to figure out what that y or what that angle value will be. So which one of these sine divided by cosine will end up giving us negative 3 square root of 3. So I'll give you guys a, couple seconds here to try and see which angles are looking, that they might be the ones that might give us the correct answer. And obviously, since you can see there is a negative sign, that should also help you out in narrowing your choices down. Okay, so let me know once you have an answer that you think might be the right one. Okay, Savannah, I see you've got negative pi over 6. So basically, again, you can use, and let's use a different color here. You can basically look at these values with the pi over 6. And, of course, making it negative is as simple as changing from the counterclockwise to the clockwise direction, right? So that's basically where the negative will come from. So your sine value is 1/2. Your cosine value is square root of 3 divided by 2. So, okay, let's imagine this is where, one of these angles is negative, either sine or cosine. So how do we go from here to negative square root of 3 over 3? So remember, this is where we do negative 1/2 and then change division to multiplication, invert the second fraction. So this will end up becoming 2 over square root of 3. And in this case, 2 and 2 will cancel out. You are left behind with negative 1 square root divided by square root of 3. We always rationalize our denominator. So we would multiply both numerator and denominator by square root of 3, which would end up giving us negative square root of 3 on the top. Square root of 3 multiplied by square root of 3 comes out to be 3. And we do actually end up getting negative square root of 3 over 3. So that means, very nice, Savannah, we would have to do, well, let's go back to our other screen so I can actually see it a little bit better. So in this case, we would say, well, the y value has to be negative pi over 6, because for a y value of negative pi over 6 is the only time we will end up getting negative square root of 3 over 3. So this answer here would be negative pi over 6 for number 20. So with the tangent function, you have to do a little bit of calculation because you won't be able to come up with the direct answer unless you're using like a table or something where you already have the sine and cosine functions listed out for you. So questions on number 20 over here, guys. Okay. Alrighty, let's go ahead and clear this out. And again, you've got several examples in your handout and your video lectures to kind of see how some of these can be broken down. These ones here obviously are very straightforward. They're just asking you to get an approximate answer. So when they don't need an exact value and they say an approximate or a decimal answer, obviously throw this into your calculator and you will see some examples like this over here. So you can see they are saying use a calculator to get the approximate value and you're rounding it to 2 decimal places. What's the only thing you got to be careful about when you're using a calculator?
Well, do we need to worry about the radian and degree modes?
Yes, you do. Chris, you were saying something. Andrew, very nice. Yeah, so you got to be careful about is the angle, because remember, this is still talking in terms of angle measurements. Is this going to be in radian or degree mode? So just be very, very careful about that. So just as a, to make sure you guys are on the right path, how about we look at 23 and 25. So let's start with 23. What answer do you get for arc cosine of 0.37? Okay, arc cosine of 0.37, and let's see what you guys came up with. Okay, I see Andrew, Savannah, Lucy, yeah, and you're rounding it to 2 decimal places. So you get 1.1917, which would be 1.19, and you can see that right over here. Let's see for number 25, arc sine of negative 0.75. Yeah, and it still has to stay in the radian mode in this case. So I've got, let's see, Andrew, Darren, Savannah, very nice. So doing this as an approximation again. Negative 0.8480. So when we round this to 2 decimal places, it becomes 85. Lucy, yeah, very nice. And then again, you can do a quick check on those. So as I said, the calculator parts are easy. You just have to remember the correct mode on your calculator, but otherwise you can do any of these, where they're asking you for the approximate answer, and you can get those without any problem. So you can kind of see here in this key, they're telling you, just make sure your calculator is in the correct mode. Okay, now let's talk about compositions with these inverse trigonometric functions. And again, we have done compositions in a college algebra course. So if that is something you again need to go back and review, you can see section P.10 is also going to be where you can review these concepts. So the idea here is, guys, when you actually take the composition between a function and its inverse function, you always get the answer of x, because the idea is kind of, if you use that same idea of they cancel each other out, they're going to cancel each other out, and you're just going to get the domain that is left behind, which will be the x value. And so that's kind of what they're talking. So you can see you can do the original function on the outside, the inverse function on the inside, and we still get x as the answer. Or you can do the inverse function on the outside and the original function on the inside, and you still get x as the answer. So like I said, think about it as them canceling each other out, and you just end up with the value you started at, which is going to be your x value. So we will pick up from here next time, guys. So we'll start with the inverse functions, do a little bit of examples with these just to make sure you guys are comfortable, because some of these we are going to have to worry about what the domain and range of these functions is. So you won't just always get this most straightforward answer. So this one will take a little bit more time for us to go over. So we'll pick up from the inverse functions over here next time, but you can see that's kind of the last thing we have to talk about. And then some of these examples here. And then after that, the last section, and I love this section because this is where we now actually get to use everything that we have learned right from section 1.1 to 1.7. So we actually get to try these with different applications. So that's kind of where section 1.8 will take us. So we'll finish that remaining part of section 1.7 and we'll do 1.8. So your second exam from sections 1.5 to 1.8 is now on Monday, March 7th. So just in case those of you who were not here at the beginning of the class, just to remind you again, don't worry, it's not Wednesday. We've moved it a week from today. So please make sure you get all your homework completed. Make sure you have 90% on each homework section and 90% attendance to take that exam next Monday, okay? So if you want to stay back and ask any questions, guys, you can. And if not, I will see you on Wednesday afternoon. So have a wonderful evening, guys. Be careful. Thanks,
You
Andrew.
too.
Take
Thank you
care.
so much.
Thank you, Lucy. Bye, guys. Take care.